Scary Rides Incorporated has hired us to create a new thrilling design for an amusement park. Before creating the model, it is important to discuss the requirements and restrictions the roller coaster will have. The descent time from the highest point to the lowest point must be minimized. As well, the client has requested the roller coaster have special features such as loops and twists. The company has also requested 3 different design proposals for the falling portion of the roller coaster. The project will have several different stakeholders such as engineers, riders, the amusement park, roller coaster manufacturers, and the government. It is important to list the stakeholders for the project as they each have a specific role for the roller coaster to be successful. The project will also have several constraints that could impact the design. For instance, time constraints, specific instructions, due dates, budget, weather, and given materials are all issues that could arise. For example, wind is a factor when considering the location of the roller coaster, since it could restrict the roller coaster from reaching its maximum speed. As a result, the roller coaster would be located in an area that is known to have a small amount of wind. The roller coaster will be designed using the Brachis-de-Crone problem as well as basic calculus principles. The roller coaster, during the design process, safety and building codes must be considered. The roller coaster must have the correct measurements to assure a safe ride. As well, the roller coaster will be tested before it is used and have recurring inspections by the government.
The group will be using the Brachis-de-Crone problem to solve the path of quickest trajectory for the drops. The Brachis-de-Crone is one of the most interesting and famous problems in experimental physics, and it's composed of the 2 Greek words brachistos and chronos, which directly translate to shortest and time. The original idea of the problem came from the Swiss mathematician Johann Bernoulli, who had the idea to find the quickest way to get from point A to point B in a vertical plane. The math problem is an example of an optimization problem, as the goal is to determine the fastest way to drop in a descent. However, it is set to a much more complicated degree, as there are many different trajectories that must be considered during the drop. Bernoulli was able to solve the problem in 2 weeks and published his findings in the year 1696 and showed it to mathematicians across the world as a challenge for them to solve it too. He showed it to mathematicians including Isaac Newton, G.W. Leibniz, Guillaume de l'Hopital, and Jacob Bernoulli, who's in fact his younger brother. There are many different variations to the solution, as many mathematicians use different methods to solve the problem, yet they all came to the same conclusion that the cycloid is the quickest path of trajectory to get from point A to point B in a vertical drop.
Surrounding the solution to the Brachis-de-Crone curve, which is the curve used to model the path of the roller coaster's quickest descent, the group has discovered that the most efficient solution is modeled by a cycloid, which is the path of a 2-dimensional sphere or 2-dimensional circle traveling along a 1-dimensional line while rolling. So far, the group is only in the research phase surrounding the steepness and length of the roller coaster's drops, but we plan on creating 3 models of varying steepness and length so that the customer's requirements may be satisfied regardless of the limitations that they impose on us. Going forwards, the team will work on developing a more concrete understanding of the complex mathematics required to model this curve, including developing an understanding of calculus of variations and optimal control. From there, the group will work to apply the mathematical model to the real world, taking into account factors like friction and drag that might affect the roller coaster cart, as well as the shape of the cart itself and the shape of the roller coaster.
There are 3 potential drop variations that our team could implement: a tall and steep drop, a short and shallow drop, and a tall and shallow drop. The first drop will have the fastest time and the fastest acceleration, probably making it the most scary. The second drop will be a lot slower and have a lot acceleration and is more geared towards those who can't stomach a faster roller coaster. Finally, the third drop will also be very quick, but it won't have as fast a time or as acceleration as the first drop. Now, on top of the drops, to make the roller coasters more exciting, we will include features like loops, dips, and bank turns. Now, to test the models, we will use a scale model and analyze the velocity, acceleration, and time, and we'll most likely end up using the first drop.
In order to proceed with solving this problem, we will use the research done for phase 2 and phase 1 into the Barkista-Cohn curve and solve the curve. Choosing the best solution to the problem, which will most likely be the steepest in order to provide the most scary ride, we will proceed forward with modeling the roller coaster. In order to model the roller coaster, we will find 3 other features to make the ride more enjoyable for the rider. Once we have decided on our features in our drop, we will build and test our model. To build and test our scale model, we will be using Beamish Monroe facilities and our budget provided to buy materials and build a scale model. Some possible materials we have thought of using are toilet paper rolls, rings on wires, and depending on how much COVID restricts us, will depend on how large our scale model is.
Throughout the remainder of the semester, the group will continue to work together on the project solution that has been decided using knowledge of the Barkista-Cohn curve, research-based information, and will also include features for the ride as stated in the initial project requirements. As the semester approaches its halfway point, the group will soon be able to work in person together to collaborate and develop the solution. A scale model for the roller coaster solution will be built in the remainder of the semester by the entire group, with its features and design shown clearly throughout the model. Throughout the remainder of the semester, there will be due dates that the group will work towards and abide by, as well as continue to follow these dates set out at the beginning of the semester. The group will work together until the end of the semester where a scale model of the proposed solution, as well as continuous knowledge gained throughout the process of the build, will be presented in a professional fashion. The group will receive feedback as the semester progresses and continue to learn and improve from that feedback to build the best model possible. Each member will put in an equal and fair amount of time for both individual and group assignments, as well as contribute ideas and collaborate with other group members to ensure the project is its best.